Good evening, everyone. Welcome to the Academy's Morrison Planetarium, which, like the Academy and Golden Gate Park and all of San Francisco, is located on the traditional unceded homeland of the Ramaytush Ohlone people, who are the original natives of the original inhabitants of the San Francisco Peninsula. I'm Bing Kwok. I'm the Assistant Director of Morrison Planetarium. Thank you very much for joining us tonight. It's good to see you all as usual, and we hope you're doing well. We also want to extend a special welcome to our online audience of Academy members and donors viewing on the Academy's membership portal. Now, we've just opened a new show. How many of you knew that? Not enough. It opened last week on Friday. It's called Spark, The Universe in Us. And before we get into that, the Dome is not the only venue that we have. I'd like to mention a couple of other presentations that we are offering. As many of you know, we've also been having a short presentation called The Sun and Space Weather in Hoffeld Hall, just below where you're seated right now. And that show focused on solar eclipses in advance of the eclipse that occurred on October 14th. But now that eclipse is over, even if we didn't see it. Even though that eclipse is now over, the show is refocusing on the sun's magnetic field and how it interacts with Earth. And earlier in the mornings, we've got another show that is geared toward our youngest visitors. And that one is about the moon, its phases, and how we went there 50 years ago. The show is called Moon Explorers. So if you've got really young visitors, really young people in your family that you'd like to bring along for their first astronomical theater experience in something like a planetarium down in Hoffeld Hall, that show is every day at 10:40 rather. Tonight's talk and next month's talks are both connected to our brand new planetarium show about the cosmic origin of the elements that make up the solar system and Earth and life. Ryan is going to introduce tonight's speaker in a moment, but the next speaker, next month on December 4th, is going to be Dr. Carl Fields, who comes to us from the Los Alamos National Laboratory, and his talk is entitled The Remarkable Death of a Massive Star. There will be no talk in January, but on February 5th, we will host Marcia Ricci from the University of Arizona, and her talk is entitled The Hunt for the First Galaxies. On March 4th, we'll have Scott Miller from NASA Ames Research Center. He's going to talk about the Starling project, not Starlink, but Starling, which is another program that, not to be confused with that other one that has to do with a whole lot of satellites. This also has to do with a group of satellites. Starling is a group of 4 satellites that were launched back in July, and this program tests how satellites can autonomously work together as a cooperative swarm. Although, I don't know if 4 is a swarm. Maybe it's a small flock. On May 6th, we'll have Alexandra Teterenko from the University of Lethbridge in Alberta. She studies the super high-speed jets that are ejected by stellar mass black hole systems. That'll be an interesting talk. And then just as an early preview, on June 3rd, we'll have Dr. Eileen Gonzalez from San Francisco State University. And her specialty is the atmospheric studies of low-mass stars, brown dwarfs, and exoplanets. So we've got a good lineup for you for the next few months, and there's, of course, more to come. All the preceding are posted to the Dean Lecture page of the Academy's website, and tickets for the next few are currently available. And now to introduce tonight's speaker is the Senior Director of Morrison Planetarium and Science Visualization, Ryan Wyatt.
Well, good evening, and thank you for coming out this evening. It's a great pleasure to introduce this evening's speaker, in large part because of the role that he played in our current planetarium show, Spark, The Universe in Us. But a little background. Dr. Enrico Ramirez-Ruiz started his educational career at the Universidad Nacional Autónoma de Mexico in Mexico City, then went to Cambridge in the UK, where he worked with Martin Rees as his graduate advisor, before a stint at Princeton at the Institute for Advanced Study, and then landing here at the University of California, Santa Cruz in 2007. His work you'll be hearing about during the presentation, and his awards are too numerous to mention, but I will mention briefly that related to the topic of his presentation tonight. He received the Mid-Career Award from the American Astronomical Society High Energy Astrophysics Division for exactly what you'll be hearing about this evening. He also received a Presidential Award for Mentorship in Science, Mathematics, and Engineering. But it's especially great to have Enrico here because he played a key role in helping us shepherd a very complex topic for the show, Spark, the Universe and Us, the story of where elements that make up you and me and our planet came from, and to find a story through that relied on the visualizations and data that make up all of our shows. You'll see a couple of those during his talk, but please welcome Dr. Enrico Ramirez-Ruiz.
I can hear my voice. Wow. Anyway, welcome everyone. It's a real pleasure being here. Thank you, Ryan, for inviting me here. It's an incredible pleasure. We're going to actually see some of the simulations that are going to play in Spark, or are playing in Spark. So I'll try to guide you through this. I really want to talk about cosmic alchemy. So I'll tell you a little bit about the history of the formation of the heaviest elements in the universe. That will be the topic of today. But before, I wanted to take you a little bit on a journey of who we are. So we have about 10 to the 28 atoms in our body. That's a 1 followed by 28 zeros. So we have more atoms in our body than stars in the universe, than grains of sand in the entire Earth. And those atoms are incredibly durable. They've been here for a long, long time. If your hydrogen atoms can speak to you, they will tell you about the Big Bang. Yeah, because they were catalyzed in the first few minutes of the beginning of the universe. Now, we are rather self-centered as humans, so we have to ultimately talk about the element, the most important element, which basically makes the vast majority of our mass, and that's oxygen. Yeah. What is shown there is really our composition as humans in terms of percentage by weight. So oxygen, carbon, hydrogen, and nitrogen. Those are the elements that are most important to us in terms of our composition. So I'm going to tell you a little bit about the history of oxygen. Oxygen is actually the big protagonist of Spark, the show, because ultimately it's intimately linked to us. So I'll tell you more about its history, and its origin story relates to the origin story of massive stars. These stars are about 10 times the mass of the sun. They have about 1,000 times the luminosity of the sun, so they're incredibly bright. They're sort of, if you are from Mexico, I can say Pedro Infante, which maybe doesn't mean much to you, but I can say Elvis Presley, for example. So they're, were incredibly luminous, but they have short lifestyles. No, so they live for short periods of time, but they're really the vast majority of the luminosity of galaxies is actually linked to these massive stars. And what we're going to play now is going to be a video which I will narrate, that comes from Spark, about basically what happens with these stars as they're basically consuming their fuel. Now, iron is the most bound nuclei in the universe, so that means that stars burn all the way to iron, and that reaction is ultimately an exothermic reaction. So burning actually gives heat. Heat gives pressure to stars, and stars are able to fight against gravity in ways that are effective. So what you're looking at there is sort of the last stages of burning of a massive star as it almost completes its burning cycle, and the vast majority of what you see in the core is the iron. Yeah. So what's going to happen when the star ultimately completes its burning cycle? gravity is going to win because no longer burning is going to be able to fight its its gravitational battle is lost, and gravity is going to create the collapse of the core. And that's going to give rise to what we know as a supernova. So what this computer simulation shows is the last stage of burning of a massive star. This is a simulation by Carl Fields, who's going to be here in a month. And we're going to ultimately enter into the core and try to understand what is happening. So the core starts to collapse. What you're seeing there is the formation of a neutron star, the densest object in the universe. So the collapse is halted by the formation of this neutron star, which basically is able to hold the collapse, creates a huge amount of energy. What you're seeing there is the large, temperature fluctuations in the core as material collapses into this newly formed neutron star. Heat starts to build up until almost like a pressure cooker. Enough pressure is built up that the explosion takes place, the collapse is halted, and a shock wave is produced. And it is in that shock wave where oxygen atoms are produced. As the shock wave moves, that's the origin story of your oxygen atoms. And what I'm going to tell you is that in your body, there's the history of about 100 million of those supernovae. Now, not only is the origin story of our bodies, but these explosions are incredibly bright. What I'm showing you there is an image before and after the explosion that happened in 2012. And what you can see is one of these supernovae is as bright as the entire galaxy put together. And just to give you a feeling, there's hundreds, of millions, if not billions or tens of billions of stars, in that galaxy. And the entire luminosity of the galaxy is dwarfed by one of these incredibly bright supernovae. So we can trace our origin story to other galaxies, and this is going to become incredibly important to our story. Now, I selected oxygen because oxygen is constantly recycled in the Milky Way and in galaxies. This is an astronomical image of a nearby galaxy where we also happen to see another supernova, 2014J, that it's actually deeply embedded into the dust in the plane. And what I want you to think about, because this is going to become central almost at the end of the show when I tell you a little bit about the genealogy tree of your atoms, is that these oxygen atoms are constantly recycled across the Milky Way. You can imagine there's a supernova in a galaxy like that maybe once every 10 years. It produces newly synthesized oxygen, and that oxygen is constantly mixing in the galaxy. Yeah? And this is going to become central to our story. Now, if we think about kind of nearest supernova remnants, so these are explosions that happen within our human life. Many of them have been seen by our ancestors. And what you see there is how a supernova looks at about 1,000 years old. And what you're seeing there are oxygen atoms, the newly catalyzed oxygen atoms in the supernova remnant that ultimately will be mixed, and they will ultimately become part of your body. And this idea is central to the show, because in the show we have to really highlight this idea of the constant recycle of atoms in the universe. And the way that you should think about our origin story is that those atoms came all the way together until the cloud that ultimately led to the formation of the sun. Yeah. Now, the beauty of oxygen is that oxygen is vital in our atmosphere, but it's also constantly recycled. I have the honor and pleasure to be sitting here, and I'm actually stealing some of your oxygen atoms. So we go through about 300 liters of oxygen every day. So if you think about it, the vast majority of the atoms that are currently in your body were not there when you were born. We are constantly recycling our atoms in our body. Now, because the atmosphere doesn't lose much oxygen, you can then start thinking about, oh, what about our ancestors? How many atoms in my body exist that once belonged to Frida Kahlo, for example? Well, the answer is about 100,000. 100,000 atoms in your body were once in the body of Frida Kahlo. So if you feel not very creative in the morning and you really have to reach down deep to think about how to get inspired, just reach out to those atoms. Now, remember, atomically, we're incredibly numerous. We have 10 to the 28 atoms. So this is, of course, a small but important proportion, and you can do your genealogy tree yourself in terms of the people that you want to share atoms with. You also think about the people that you don't want to share atoms with. So you can not listen to those very carefully. But the idea of who we are, it's ultimately linked. So, the idea that the show had is to basically think of ourselves as this cosmic constant recycling of atoms in the universe. So you can think of us, cosmologically speaking, about our origin story. But I also want us to think about that our humanity is intimately linked to each other because we share oxygen atoms constantly with each other. No? So when you think about things that separate us rather than unite us, I hope you start thinking about kind of our common ancestry, atomically speaking. So the central theme of the story today is how elements heavier than iron are formed. There's a cartoon there kind of trying to think about the essence of how these elements are formed. If you look at a periodic table and you look at iron has the same number of neutrons than protons. But then if you look at elements that are heavier than iron, you require a larger proportion of neutrons for them to be stable. So almost the vast majority of atoms above iron are actually produced by neutron capture of neutrons. And the story that I'm going to tell you is how we make about half of those elements where the capture has to be so incredibly fast that we're going to require the most extreme conditions in the universe to take place. So we are certainly thinking about alchemy in the universe. And here I highlight 3 elements that are going to be essential to us, to the story. Uranium, platinum, and gold. Yeah. And I sort of selected these 3 elements because they're going to become really important to our narrative. What I'm going to try to convince you is that these elements are indeed essential to life. And that's also a center theme of the planetarium show. Even though these elements are incredibly rare, they're essential for our survival as a species, and hopefully I'll convince you there. But there's some hints there that has to do with the Earth's magnetic field. Without these elements, we would not have our shield. We would not have magnetic field surrounding the Earth, which of course is incredibly important for us to survive, and the ionized radiation around us. But before we talk, I talk about these radioactive elements, I wanted to tell you a little bit more about gold. So of course, gold is the most noble of all metals. That's why it doesn't get corroded. That's why, we use it for jewelry. And if you think, well, why is gold important to me? Okay, you convince me oxygen maybe because it creates a significant fraction of my body. Well, you have about 10 to the 18 atoms of gold in your body. Yeah? So that's about, 0.2 milligrams of gold. So, and a gram of gold is about $10. So, but, we have a significant fraction of gold, but not very large. And I'll tell you, relative to the universe, how much gold you have. But this is just to make it important. Now, I'm going to guide you through an incredibly important scale when it comes to composition. So I wanted to kind of put in your mind what 1 part per billion looks like. Yeah, so that's going to be our unit for the fraction of gold in the universe. And I thought this analogy makes it clear what 1 part of a billion is. So imagine that you have an Olympic pool that has about 660,000 gallons of water, and you take a teaspoon and capture it. That's 1 part in a billion of the entire swimming pool. That's amount the composition of gold in the universe. So I have created this table here that tells you, well, the universe had about 0.6 parts per billion. The sun has about 1 part per billion. That's primarily where our scale comes from. Meteorites are hundreds of times more abundant in heavy elements. So if you heard about going and mining asteroids, one of the reasons is exactly that they have a significant proportion of their mass being these heavier elements. The ocean has about 0.05 particles per billion, and in fact, it contains the largest reservoir of gold on Earth that still hasn't been mined, and hopefully will never be mined. But yeah, the vast majority of gold that was available to us on the surface has been mined and is in a vault somewhere. But us humans are incredibly more abundant in gold than the universe and the sun. Again, if you start thinking that you don't have as much blink as you think you do, you do. And if you actually like sushi, for example, or eat large fishes, then you will have a higher proportion of gold in your body. So the story today is the origin of gold, the origin of these very, very heavy elements. And I would not make, I want to kind of highlight my ancestral myth of where the gold came from. So the Aztecs believe that gold was the sweat of the sun that just came down to earth. And these gold nuggets that you pick up, so you can challenge me and say, oh, Enrico, 1 part in a billion, and then you find these gold nuggets on Earth. What's going on? Well, the issue is that in these high-density pressure environments, they get drastically concentrated. Yeah, and that's why gold mines are in particular spaces on Earth where this concentrated magma comes about. And this 1 part in a billion becomes much more highly concentrated. Now, the Aztecs were right. The sun has a lot of gold, but it wasn't created there. And what I'm actually going to show you at the end of my talk is that, in fact, the myth of the Aztecs was actually relatively correct. So we'll tell you a little bit about how the gold arrived to the surface of the Earth. Okay, so if you want to make a gold recipe, you need 2 of the densest objects in the universe, 2 neutron stars, and I'll tell you a little bit more about them. You need to basically cook them at about 1 billion degrees. Yeah, and in the process, they will make a black hole. But in that process, the vast majority of heavy elements will be produced. Yeah, and I'll tell you how we now know that to be the case. So one of our protagonists, going back. So this is a neutron star. It is the size of Manhattan or the size of the San Francisco city. Yeah, it's only about 8 miles, but it has a larger mass than the sun. So if the density of water in some units is 1, the density of a neutron star is 14 orders of magnitude denser, 1 followed by 14 zeros. So the nuclei are basically touching each other. Now, if you were at the surface of a neutron star and you wanted to escape its gravitational pull, you will have to move at 30% of the speed of light to be able to leave its gravitational pull. So these objects are incredibly compact. They also, neutron stars belong to generally binary systems, and a smaller fraction of those neutron stars live with another neutron star. They spend their entire cosmic life together. And it is those pairs that are basically the central protagonist of our story. So before we show you this in the beautiful dome, I wanted to sort of give you an insight of what we expect. So these objects are so incredibly compact and dense that the distortions of space and time are so large that they produce these gravitational waves that you see there. And those gravitational waves carry both energy and what we say angular momentum. And what happens is that this system is basically coming together slowly, and these beautiful dance last of the order of 100 million years to 1 billion years, depending on the initial separation of the systems. But then these objects get so close to each other that they merge. And it is in that merging where we think the vast majority of these heavy elements are produced. Okay? So this is the artist's rendition of a neutron star. And what you're going to see is the distortions of light that the two neutron stars are basically taking place. I'm getting dizzy here. As they basically come together. So this is the visualization in the show that will trigger the formation of these incredibly essential heavy elements. And as we go from this visualization, which is physically inspired, we're going to turn into a simulation where the two neutron stars merge. And if you see these tidal tails that emerge from that, a fraction of a solar mass in these tidal tails ultimately turn into newly synthesized heavy elements. And all of this merger happened in the order of milliseconds. Whoa. I think they're playing it again. We didn't plan it to play it twice, but it's okay. You should enjoy it again. And what we believe is that when these two objects merge, they will ultimately collapse into a black hole. The mass of the merged remnant would be just too massive to be supported, and a newly formed black hole will be triggered. So one of the predictions that we made is as these tails are ejected, they produce these heavy elements which are radioactive, and as they decay radioactively, we think that they will produce light. And we predicted that they will produce a transient, really in the infrared bands, but close to the optical, that will fade within about a week. That was the prediction that we made. And both the fading law and the spectrum will tell us whether or not these heavy elements will be produced. We knew the decay of these heavy elements very well, so how the energy will be injected. And we also will know that these elements are so complex atomically speaking, they have so many lines, millions of atomic transitions, that we were able to predict before we saw them more or less how the spectrum would look like. And those two components, both understanding the basically luminosity or brightness as a function of time as well as the spectra, gave us the clue that indeed we were witnessing the formation of these heavy elements. So how did we find them? So August 17, 2017, that I think after the birth of my kids is probably my favorite date. LIGO, the LIGO interferometer, detected gravitational waves from a pair of neutron stars. You can see there, what you're seeing there is the frequency of the waves, and of course, as these objects get closer and closer, they are high pitch. So the pitch is increasing, so they're higher and higher frequency. And as a function of time, they get basically louder, but also higher frequency. And that's exactly what LIGO was able to see. And I'm going to tell you a very interesting story that I think changed the life of many, many astronomers. I don't know if you see, so these this is the uncertainty in the sky that the gravitational wave detector says. We saw a gravitational wave coming from somewhere there in the sky. Now, they call them banana-shaped structures. So I want to take a second to try to give you an insight as to why they are this shape. So gravitational wave detectors work very similar to your ears. They actually detect the amplitude of the wave, the distortion of the wave as they go by. Yeah. And we had 2 gravitational wave detectors across the United States. So imagine that you close your eyes, yeah, and you think about, can I actually differentiate whether the sound came from the front or from the back? And the answer is you cannot. This plane of symmetry that we have in between our ears makes us basically completely unable to tell the direction of sound. And the same happens from the gravitational wave detectors. And so these banana shapes that you see there is because that's the uncertainty. They say they came somewhere in that plane, but we're unable to tell where exactly. But then if you look at GW170817, astronomers are not very inventive when it comes to names, that's just the date. You can see that the banana shape drastically got reduced. Significantly. So as astronomers, if you're actually going to look for light, you better get as accurate position in the sky as you possibly can. So what happened? 3 days before this event happened, a 3rd gravitational wave detector turned on. So rather than having 2 ears, we had 3 ears. And if we had 3 ears, we'll be able to place the position of that sound significantly more accurate. 3 days. And that basically changed the course of history because we were able to localize this event in a much more effective way. Now, I'm part, again, when we continue to talk about names that are not very creative, of a group that it's called the 1 meter 2 hemisphere collaboration. Why? Because we have 2 1 meter telescopes, one in the north and one in the south. One is in Lick Observatory, very close to us in Mount Hamilton, and one is the Swope Telescope in Chile. Why? Because gravitational waves don't discriminate between the north and the south, and you have to basically cover both sides and say, we don't really know where the gravitational wave is going to come, so we have to basically cover both hemispheres. But the story is actually quite interesting because we were competing with much more powerful telescopes, particularly the Blanco 4 meter Deccan telescope. It's a 4 meter telescope, so they have 16 times the collective power and 12 times the field of view. That were our competitors. So I tend to think about this discovery as the David and Goliath story. Yeah. And one of the things that actually allow us to be the first one to discover the electromagnetic signal from this event is that because we decided not to look at the entire sky, but only to the galaxies that were within the volume that you saw. So the gravitational wave signal gives us the distance, and you saw the banana. So now you can actually imagine in 3 dimensions. We know exactly all the galaxies where this event could who could come, and because there's a lot of empty space, rather than tiling or telescopes, we actually target the galaxies. And that's actually what gives us the edge. Now, this event was incredibly interesting because when it happened, you can see there was basically, in Chile, there was basically bright light. If this was actually, if there would have been telescopes in Africa looking for this event, they would have seen it. But they didn't. So we had to wait until basically the southern hemisphere was basically dark to start the observation. So what I'm going to show you here is sort of our observational strategy in trying to find the light coming from these 2 mergers. So this is work that David Coulter, who's a grad student at UC Santa Cruz, developed. And what you're going to see there, the pointing there that you see are the galaxies. So what we try to do is maximize in one pointing to get as many galaxies as possible that belong to that volume. But not only that, rather than pointing to all galaxies, we pointed to the most massive galaxies because they have the largest number of stars. So we say they're going to have a higher probability of hosting this event than the others. And as you can see, because we actually beat all the teams by about 1.5 minutes, that strategy was actually incredibly important. So there you go. This is our observing a strategy. So 51 minutes after sunset, as fast as you can do as an astronomer to observe. And you can see how quickly. So 10 hours, 50 minutes after the trigger, but in less than 10 minutes of observations, based on that strategy, we were able to actually see the electromagnetic counterpart associated with the gravitational wave signal. So for the first time in the history of astronomy, we detect something through a new type of event, gravitational waves, and then also through the electromagnetic waves. And this is how it looks. This is the host galaxy, which, if you're familiar with galaxies, it is a fairly large dead galaxy with a lot of stars. And the object that you see there was originally very blue, but the prediction was that as a function of time was going to turn very red. Why? Because it was the telltale signature of the complex atomic structure of these heavy elements. And that's exactly what we saw. So I want to highlight here the discovery team. In particular, so Ryan Foley there with the long hair next to me. I'm the oldest individual in that, which makes me incredibly happy. We had a lot of early career scientists, an incredibly diverse team. David Coulter was a second-year PhD student with his t-shirt, "I want to believe," and he did. That developed basically the algorithm to make our decision-making tree of which galaxies we were going to look like. And because of him, we were able to actually be the first team to discover the electromagnetic signature. The person with glasses at the far right, or my right, your left, Charlie Kilpatrick, is the first person to actually see it in an image difference. So he took an image difference of that galaxy and said, "Oh, there's a transient there." So he was the first one to see it. Ariadna Murgia in the black shirt with a beautiful smile. She was the lead theorist. Worked closely with me, also from Mexico, and basically set the foundations of trying to understand the signature that we saw. So how much gold that a neutron-star merger can make? So this is the question that we tackled in that paper, which we predicted in advance, and the answer is about a Jupiter mass of gold. Yeah? Jupiter has about 10 to the 30 grams. So as I was saying, 1 gram of gold is about $10, so 10 to the $31, that's a lot of money. Now, if this is not incredibly impressive to you of how much gold this is, let me contextualize it. This is about the equivalent of gold content in about 1 million stars. Yeah, so this is going to become incredibly important for the story at the end, which is while the oxygen production of the universe happens very commonly, it happens very often, these happens very rarely. Yeah, so I want you to have this in mind about the what we call the chemical evolution of the galaxy. So how the galaxy came to be, and you're going to see a beautiful visualization of that. So I want you to think about oxygen production as, chocolate, and imagine a chocolate cookie with a very thin layer of chocolate, very well distributed. That's kind of oxygen in the universe. Oxygen is very well mixed, and there's not large variations. Of course, those variations as a function of time as the universe matures and produces more and more oxygen get washed out. But neutron star mergers, the production of these heavy elements, it's more like a chocolate chip cookie. The vast majority of those elements are so highly concentrated that if you're a star that is born close to the chocolate chip, you will have a huge amount of gold. Versus if you're far away, you will have very little. And that's actually what we see when we actually looked at relics, a sort of old stars within the Milky Way whose metal content is very small. Early on in the universe, we find variations of gold from star to star of factors of 100. Yeah, and that has to do with basically this idea that these objects are actually very, very rare, but produce a huge amount of metals. And, this was beautifully highlighted as the 2017 breakthrough of the year in science, and we were incredibly proud that half of the articles of that, of that issue were basically led by early career scientists at UC Santa Cruz. So what I want you to think about before we actually looked at this really beautiful visualization is the idea of mixing. So similarly to us sharing our oxygen atoms constantly in this room, astronomical events happen in the galaxy. They throw their freshly synthesized metals into the gas, and the gas is constantly being steered and mixed. Yeah. So if you ask, well, how many, remember you have 10 to the 18 atoms of gold. How many neutron star mergers took to make that in your body? We believe of the order of about tens of thousands of these events. Remember, when you compare with the hundreds of millions that took the oxygen, that just tells you because the rates are very different. This is a much rarer phenomena, but produces a lot of that event. So the simulation, and I think we're going to start, and I think we're going to pause it, hopefully, so that I can explain and contextualize what you're about to see. So we are basically coming into our own Milky Way. Of course, this is a simulation. Perfect. So it's actually paused. I don't know if you can see, there's like a white dot very close to the center of that galaxy. That, everything is going to become apparent when you see it, but that dot represents the gas cloud that ultimately create the solar system. Okay? And for you to understand the genealogy tree of your atoms, rather than going forward in time, we're going to go backwards in time in a simulation, and we're going to trace back the origin of your atoms in your body and where they came from. Okay? And then I'm going to be completely quiet while you witness this, and then we'll talk about it. Okay? So we're going backwards in time, and we're retracing, the path of our atoms in the galaxy. And the galaxy is looking younger and more messy because it's, that's how it looked when it was much younger. And we'll pause it sometime around here. So there's a few things I wanted to highlight. One is that a significant fraction of the atoms were not even produced in the Milky Way. Were produced in other galaxies that ultimately fell into the Milky Way. Yeah? So not most, but a smaller fraction of your atoms are actually extragalactic in origin. So don't let anyone tell you that you haven't been outside our galaxy, because you have. Second, our atoms have traversed the entire Milky Way multiple times. They were not all formed very close to where the cloud that gave rise to our own solar system they actually traverse the entire Milky Way many times. They traverse so many distances. And in this visualization, where we're primarily focusing in our oxygen production, which is the most common of our productions, what you ultimately can see is the imprint of hundreds of millions of supernova that happen not only within our own Milky Way, but also outside our Milky Way. And all these satellite galaxies that ultimately made the Milky Way progressively more massive are also imprinted in your body. Now, if we would have solely focused on the atoms of gold, the number of tracks will be much smaller, yeah, because there are fewer of these events. And of course, this for visualization purposes, we are only focusing on a few elements. Otherwise, it will be incredibly difficult to keep track. But in some ways, this is the genealogy tree of every single atom in your body. That's where you ultimately come from. And if you rewind all the way back to the Big Bang, you will see the hydrogen atoms coming to place. I'll do the next slide. I know it almost seems like we should stop there. So I wanted to finish telling you a little bit about why these heavy elements are incredibly important, trying to make it much relevant to you. And this is basically, there's two elements, both uranium and thorium, that played an incredibly important effect in the Earth. As you know, the Earth's core is warm, and it's actually warm because of radioactive material. But these two elements have radioactive decay timescales, or half-life times, that are long enough that today are the main contributor of the heating rate in the core of the Earth. And what we know is that these elements are essential to life because the interplay between the convective motion and the rotation creates the magnetic field on Earth. So I want you to go back to this chocolate chip cookie analogy and think about, well, even today, we can find two solar systems that are identical, but they have a factor of 3 difference in their heavy element content. So the question is, what will happen to the Earth if the radioactive heating was twice as intense as it is in our own Earth, or the radioactive heating was 2 times less? So this is the exercise that we played. And what you see there is if you have more radiogenic heating, you will have extreme volcanism, but you will not have a dynamo. What means that we will have an Earth-like so-called habitable planet without a magnetic field. And we'll make it, I can assure you, non-habitable. Earth-like seems to be actually in a fairly comfortable position in the sense that it seems like the radioactive heating that we had was able to build our magnetic field, but also give us volcanism, which is also incredibly essential to our atmosphere. But if you look at other stars like our sun that have Earth-like planets, if they have less radiogenic heating, they could in principle have a magnetic field, but they will be geologically dead. And then the question is whether or not, even with a shield, where life could in principle exist. So I wanted to sort of end with, I wanted to give you one important message, and it's the message that is intimately linked to the origin myth of the Aztecs and gold basically raining down from the sun. So for a long period of time, I keep going backwards. Geologists were incredibly puzzled as to why is it that we can find gold in the surface of Earth. Why? Because when the Earth was made, which is highlighted today, and molten Earth, when it was made and it was molten, the vast majority of heavy elements sank into the core. That's one of the reasons why uranium and thorium are so incredibly effective, because they actually, since they're heavier, they sank into the region where most heat is needed. And for a long time, it was really a mystery to think about. And what we now know is that most likely, at the time of the large bombardment where the moon was formed from a giant impact, a lot of these small bodies that landed in the surface of the Earth brought with them these very heavy elements. And you remember that they are much higher in their abundance of these heavy elements. So they ultimately created these heavy elements, which in the mantle of the Earth were then mixed. Yeah? So that's where we think about the origin story. And just to finalize my talk, I wanted to give you a myth that was told by my grandfather, who was indigenous Chichimeca in Mexico, that I think is actually really beautiful and fits with one of the ideas that Ryan and I and many others that work in this planetarium wanted in the show wanted to convey. So my grandfather basically says, in this myth, when you're born, your essence came rushing down quickly to you, similar to gold hitting in the surface of the Earth. But as it came to you, it actually broke into many pieces. And it says when you gain consciousness, you're going to feel kind of incomplete. But life has given you an opportunity, because those pieces were not just scattered across the floor, they actually fell into other people. And only by sharing those pieces, you're going to become whole. And in that journey, you're going to find people that have these incredibly large pieces that are going to make you incredibly whole. But in your journey to being whole, every single human matters, and your interactions with them are incredibly important, because if you're not able to share those pieces, you will never ultimately become whole. Yeah. Which I think is a beautiful way of ending this story, and a way of thinking about part of what we wanted to capture in this show was thinking about our humanity and the things that actually make us human rather than the things that separate us. And thinking about our own cosmological myth and origin in thinking about the history of our atoms and the history of our shared atoms, and the fact that when we even think about ownership of our own atoms, we don't even have that ownership because we share them constantly throughout humanity. So hopefully when you see a gold ring again, you will think differently, and you will think that it took the most extreme densities and temperatures to make that gold, and that ultimately the same heavy elements are really essential to protect us. And I'll stop there, and I'll thank you for your time.
Well, thank you. We'll have a time for some Q&A. If you have a question, if you could raise your hand, Bing or I will come and deliver a microphone to you so that everyone can hear your question. We do have people online as well, so people who want to hear the question. And while we're handing out the microphone, I'll just note, Spark shows daily in Morrison Planetarium for now, basically for the next year. So please, if you haven't had a chance to see it, come by and see the whole show that you've heard a bit about this evening. The first question from the third row.
Dr. Ramirez-Ruiz, thank you for your amazing, incredible presentation. I think I heard you correct that when two neutron stars collide, they likely produce a black hole. So that means a lot of the matter gets sucked down into a singularity, and then a lot of the matter gets blasted off into the cosmos in these forms of heavy metals. Can you give a description, if you have like two solar masses, neutron stars colliding, what percentage gets sucked down into the singularity and what percentage gets blasted off into the cosmos?
Yeah, I think if I had the answer to that question, I'll be. This is a really open question in astronomy. What happens to this object? So let me give you first something that I think is actually fascinating. So when these objects come together and merge, a significant fraction of their mass, the rest mass energy, is radiated in gravitational waves. So they are lighter by the time they come together. Now, the equation of state for nuclear matter cannot sustain, we think, the weight, and it will ultimately collapse to a black hole. Now, because there's significant amount of rotational support, we think that a lot of this material will basically be around. And a lot of the hope is that kind of heating in what we call an accretion disk can actually eject more mass than the mass that goes out in the tails. So the way that you should think about it is when these two objects come together, there's a little bit of material that it's able to basically get above the escape velocity as these two objects come. These are usually called as the two outer Lagrangian points. But it's only about like 1% of a solar mass. And when we actually measure how much mass was produced in this event, we get of the order of about 5% of a solar mass. So we need still, when these objects come together, to eject about a factor of 5 times, if not 10 times more material. And we actually think that it's more the dissipation and the heating that it's able to eject some material above the escape velocity of the system before everything. Now, obviously, these heavy elements, when they fall, they actually dissociate into neutrons and protons. So they no longer are gold elements. But yes, the vast majority of the gold is actually lost there. So.
Next question with the fourth row.
Yeah, thanks for the presentation. One thing I'm curious about is you mentioned that the bulk of the heavy elements are produced by these neutron star mergers. But I know that a lot of heavy elements are also created just in like single supermassive stars when they undergo supernova. So do they not like eject most of this matter because of the black hole that was from the previous question?
No, I think, so this is, of course, a matter of extreme debate. But of course, since I worked on this, I can be completely biased and tell you my perspective. Yeah, so standard supernova. So if you look at a textbook, 10, 15 years ago, it says most of the heavy elements in the universe were made in supernova. We believe that not to be the case. We're completely convinced of that. Now the question is, now there's new models that says, well, if there was a rare type of supernova that can actually make these heavy elements, can they still work? So there's a camp that are trying to do very rare supernova explosions that require, in reality, they require really kind of high magnetic fields, producing a magnetar. You really have to increase the entropy very, very drastically in these environments. One of the reasons is because the neutron stars in supernova are born hot and they have a lot of neutrinos, and that changes the composition of the type of material that you can make. So we are, of course, completely convinced that these objects do produce the heavy elements at the right rate and at the right masses to basically give you every single atom of heavy elements that we see in the Milky Way. The question, I think, that is right now under a lot of debate is whether or not these objects, because they take a little bit of time to merge and come together, can really enrich the very, very kind of low metallicity early stars, and whether or not we need another channel like a very, very unusual supernova that happens maybe once every 1,000 supernova that is very unusual. But in general, yeah, the answer is no. I think we believe that, and especially, if you really believe my chocolate chip analogy, that's actually what we already predicted, that the fluctuations from place to place in the early universe were so vast that it had to be an incredibly rare event, and it cannot be a typical supernova. But yeah, that's an incredibly interesting. I mean, if you think, for example, we also talk about iron in the show, which I didn't talk about, which some production of iron happens in standard core collapse supernova, but also a significant fraction of the iron, if not the vast majority, happens when you blow up a white dwarf. But one of them is like 10%, and the other one is like 90% of the contribution. And these two channels are incredibly different, and still they're sort of competing with each other. So it could be the case that, we can have multiple ways of producing this. But what I can tell you is that it has to be a neutron star. It has to be something around a neutron star, just because the timescales have to be very short to capture these neutrons. So either when you make a neutron star or when two neutron stars come together.
Okay, interesting.
Any other questions? Just raise your hand. We'll be happy to bring a mic to you.
And it seems like there are some online questions. Sorry.
Oh.
Hi, thank you so much for the talk, by the way.
No, thank you for being here.
So you talked about neutron star binary system mergers. Are there other types of mergers, say like neutron stars with black holes or neutron stars with other types of stars that would produce other heavy elements, or is it just these neutron star mergers that are mainly producing the elements?
Yeah, that's a great question. So LIGO started seeing two black holes where you have two black holes coming together, and of course there's really not baryonic matter, so we don't actually expect even these systems to emit any light. Now, then you can have a neutron star with a black hole. That should in principle give you very similar conditions, and we think that that could produce heavy elements, but the vast majority of black holes that we know are significantly more massive than the neutron star, and it means that the neutron star will fall inside the event horizon before it actually gets destroyed. So we won't expect in those to produce heavy elements. But that's still under debate as to whether or not we can, the vast majority of black holes that we're finding, the minimum mass is about 8 solar masses. So those are too massive. So the neutron star basically falls into the black hole and there's no ejection. No, everything goes into the event horizon. So currently, in terms of mergers, this is our best bet. Now, if you have a more massive object, like a white dwarf, or a star going around a black hole and gets disrupted, the densities are all of a sudden not very high. So that is very difficult to produce heavy elements. So you really need kind of nuclear matter, very, very compact nuclear matter in order to make these events. But it could be the case that, LIGO has, there's some hints of two objects that seem to be an object that seems probably a little bit more massive than a neutron star with something that looks like a neutron star, but the uncertainties are large enough that. But if that was true and you have a low mass black hole, then very similar processes will occur and you will be able to produce. But those are rare. So in terms of the rate production, we probably expect them not to compete with neutron star mergers.
All right. All right.
I think we're waiting for the audience. I can hear my breathing too.
Thank you, Bing. So we have an online question, which would be that neutron stars have very strong magnetic fields. Do these magnetic fields play a role in the cosmic alchemy you described?
Yeah, that's an incredibly interesting question. So for those of you that you may not know this, we discovered two neutron stars going around each other now since the 70s. And in fact, the Hulse-Taylor pulsar was basically the first object in which we were able to actually see that these objects, by timing them so perfectly, were actually coming together at a rate that was exactly what general relativity predicted. So they were creating these gravitational waves, and they were basically coming together at the rate that was predicted by general relativity. What we know is that by the time they merge, most of the magnetic fields of what we see in pulsars are not very strong. So they probably would not affect the merger. But as soon as these two objects merge, the same mechanism, this dynamo mechanism that we talked about that amplifies the field inside the Earth, actually happens there and can create incredibly large magnetic fields and will play actually an incredibly important role. Something that I didn't talk about is that these neutron star mergers, also when they merge, they produce these relativistic jets, we think, when the black hole is actually produced, and produce what we call short gamma ray bursts, which are these very, very bright transients. And we need a very strong magnetic field to do this. So we actually think that the strongest magnetic fields are produced when this merger remnant comes together. Now, we were talking about supernova, and in the alternative theory for heavy element formation, we also require very, very high magnetic fields in a supernova to increase the entropy to try to change the initial composition of what we see. So in those both scenarios, I think magnetic fields are really important. They also make really beautiful movies.
So we have a question from the back row.
Thank you so much. It was really great. I was wondering, as you mentioned the chocolate chip cookie analogy and how some stars have a lot more heavy elements than others, how does that affect the stars, like life and other stuff around them, and also how they die and maybe explode in supernovas and
Yeah, that's an incredibly interesting question. So let's, for example, go back in time, think about the Big Bang. So the universe only had hydrogen and helium. So astronomers, and I know Ryan gets offended by this, call everything that is not hydrogen and helium a metal. So for astronomers, so we call it the metal content of the universe. So something that is actually beautiful is that when we looked at stars that are very, what we call metal poor, means that they were very old. They were formed when all of these metals were just coming to life. So one of the important questions, I think, is how metal-rich a star has to be in order to make planets. That's actually a very interesting question. We think that maybe hundreds of times, potentially less than hundreds of times, but tens of times less metal content than the Earth would allow the star to make planets. And here, the vast majority of the metals that we're talking about are carbon, oxygen, iron, the ones that are much more common. So then all of these stars that have large variations in chocolate chip, in these heavy elements, yes, they will produce, in principle, they could have produced planets, but they couldn't. So that means that all of these internal heating that we were talking about would not happen there, because these stars that are very low metallicity, we don't think they will be able to make planets. So planets actually is a relatively recent occurrence in the history of the universe, where the metallicity had to grow to significant levels for planets, these rocky planets in particular, to be able to be made. Now, once planets are made, we think that the variations could be a factor of 5, maybe, not a factor of 100. But those variations, as you saw, will drastically change the heating rate in the core of this planet. So their interior will be drastically altered. So we actually think that these heavy elements, especially over longer timescales, will actually play a really, really critical role. In the early solar system, the element that was actually most important for the heating of the Earth was potassium. As you know, potassium is also an incredibly important element for life. No, like the amount of little changes in potassium in the initial cell that made you determine whether you're going to be an eye cell or a bone cell, so potassium is also incredibly important. And I know Ryan and I felt a little guilty that we left potassium out of the story.
Our next question from the second row from the top.
Thank you. I was wondering, are neutron stars being created now at the same rate that they were at the time of the formation of the Milky Way? And how common is it that binary neutron stars are formed?
Yeah, it's a great question. So let me give you some insight. So just some numbers to guide your intuition. The Milky Way, the entire galaxy, on average, produces about a solar mass of material per year of new stars. So you can almost think that every time, is your birthday, because you're incredibly special, a new star like the sun comes to life in the Milky Way. Yeah, so that's more or less the rate. And the Milky Way has been, for about 10 to the 10 years. So, and its stellar mass is about 10 to the 11, close to 10 to the 11. Now, what we call the star formation rate, which is the rate of forming stars, was much more vigorous in the past than it is today. In a sense that, galaxies that are very, very, like the JWST early galaxies, they're creating about 100 solar mass per year. So they have elevated rates compared to today of 100 times that of today's Milky Way. Now, if you take the current Milky Way rate, we produce a supernova or a neutron star once every 100 years. So that's the rate of production of neutron stars in the Milky Way. So every time, and we haven't seen yet a Milky Way supernova explosion, potentially because it's very difficult to see because, there's so much dust in the plane across that we may not be able to see it. But now actually we may even see it in neutrinos. So if there's a supernova coming soon, we will actually see it in neutrinos, even if it's completely obscured by dust. So that gives you a rate. Now, then of course you have to make one neutron star, you have to make a companion, and you have to have them stick together. And that rate is almost, 1,000 times less likely. So if a neutron star is made once every 100 years, a neutron star, that could merge, it's made like once every 10,000, 100,000 years in the Milky Way. And currently we know, and because these objects, once they're assembled, they live, close to each other for so long. In today's, we have about 20 order of magnitude, 20 double neutron stars that we've seen in the Milky Way orbiting around each other. And we see them because one of them is a pulsar. And I think the discovery of the double pulsar is really what ignited LIGO to be built, because they say, based on how many we see, we can calculate the assembly rate, and we should be able to see them in gravitational waves. And that's basically what started the gravitational wave, field of astronomy.
So our next question is from the third row.
Hello. Thank you for your presentation. I just had a question about the elements that were mentioned. I noticed some of them were also radioactive, like the heavy elements. I was wondering if there was any direct correlation between like the heavy elements being radioactive and the magnetic field produced at the Earth's core.
Yeah. So you produce a lot of these elements, but the particularly really heavy elements are certainly more radioactive. And that the reason why is because you produce so many neutrons, and neutrons decay into protons, so they are drastically more radioactive. I think that there's also an interesting coincidence that they tend to have very long half-lives, so they don't decay as quickly. So, by the time a lot of other elements have decayed early in the evolution of the Earth, these more heavy elements actually are still there present and are contributing with the vast majority of the heat. So this is really an issue of steering the course Earth that, when coupled with rotation, allows the magnetic field to be made. But yes, and in fact, if you look at a periodic table, you should do that when you go home. You should actually look at some of the very, very, very heavy elements that have been discovered. Their half-lives are very short. So they're actually only discovered in the lab, and then they disappeared. And then someone claimed, I discovered a new element. It lasted 10 milliseconds. No? So that part of the periodic table is being basically expanded that way in the lab. But that's because these nuclei are drastically unstable. And the more and more neutrons you put in, the more unstable they are. I don't know if that answered your question.
Yeah, no, that did. I was thinking about gold as well, because that was also a heavy atom that isn't radioactive. So then I was like,
a nuclei can have a multitude of like you can find stable uranium and uranium that is not stable depending on its atomic number. So there's a whole family, and some of them are stable and some are unstable, almost like a Thanksgiving dinner. Yeah.
Hi, thank you for your talk.
No, thank you for being here.
I kind of on the same note, I'm not really sure if that just answered my question, but as you were saying, in lab conditions, we're able to produce very heavy, unstable elements. So I guess the question is kind of, what's the cap on the heaviest elements that are able to be theoretically produced in a neutron star merger? Like, would unstable, not that we would necessarily be able to measure it or observe it, but theoretically speaking, could very, very heavy unstable elements with short lifespans be able to be produced in those mergers?
Yeah. So one of the challenges that we have is that a lot of the experimental data that we use for our models to try to predict what elements are formed we don't have observational support. So a lot of those are extrapolations for the models, which basically depend on how well we understand nuclear structure, which is not great. So therefore, to answer to that question really depends on theory. But experiments are getting better and better to actually try to understand kind of the phase space where these elements live. In general, yes, we expect some of these very, very heavy bombardment of neutrons to produce some really heavy elements that both either get fragmented into smaller pieces or decay very quickly. And that depends on the models. I think if you're curious in general, when you look at the abundance distribution of the sun, you're going to see different peaks where elements are actually much more common. And in elements that are made by neutron capture, there's 3 peaks, and those have to do with nuclear structure. That is when the nucleus basically complete all the levels, and you have closed shells. Then you cannot capture neutrons, and those kind of peaks coincide. So you can even look at the abundance of the sun and really understand nuclear structure fairly clearly. But there are some peaks in between that are not associated with those closed shells that we don't really understand exactly where they come from, and a lot of that is our uncertainty about nuclear structure. But something that is actually kind of beautiful observationally is that this process is incredibly robust, because when we look at the abundance pattern of stars that are very old, only like 5% when the universe was 5% of its current age, the pattern looks identical to today. So if you want to build a theory, you better have to come up with a theory that gives you an abundance pattern that is incredibly robust, and we're having a hard time doing that.
Thank you so much.
Hello, I just wanted to say thank you on behalf of my astrophysics class that came from USF. I think this has been such a valuable presentation to listen to, so thank you for your time. I guess I wanted to ask about the correlation between metallicity and magnetic fields. I guess my friend here kind of, when she asked it, I guess you kind of answered it, but I was just kind of curious to know about that, because neutron stars obviously have more metallicity than as opposed to our sun. And I guess I was curious to know what that translates to in terms of what their magnetic fields look like.
Yeah. No, thank you for being here. It's great to see you all coming here, and I'm honored to be stealing some of your atoms when I get home. Yeah, I think so. So when we think about, when we think about objects that are magnetic, I mean, a lot of what I was trying to say is these elements are not, are rare. The entire content of the sun of all of these heavy elements is maybe 1 part in 10 million. Yeah, it is kind of amazing that these elements contribute with the heating of the core, because they are rare in terms of their content or their specific number, not per unit mass. They are very, very rare. But they, in some ways, in planets, they do contribute with the vast majority of the convection. Now, in stars, these elements are not that important, because stars are convective due to nuclear burning. No? So then, whether or not a star has a magnetic field, really these elements don't play a really important role. Now, your question, I think, about magnetic fields, I think in general, the more binding energy, gravitational binding energy an object has, no? When you think about in your gravitational class, like gm square over r, like the more compact these objects are, the more energy they have, they usually can basically have a much stronger magnetic field. So what we see is that the highest magnetic fields are found in neutron stars, then less in white dwarfs, and then after in stars like our sun. And that's because the the energy density of the magnetic field can only grow as strong as the energy density of gravity. So the strongest, kind of magnetic objects are indeed neutron stars, just because they can sustain such large magnetic fields. I don't know if that makes sense, but it is unusual that the dynamo mechanism depends on these elements that are rare, and that only happens in planets, because planets are not generating their own heat. No, they're not doing any fusion in their cores. They're all radioactive. I don't know if that. But we can
Next
talk more.
question is from about halfway up, left of center.
Sorry, I have to move because of the projectors. Let me see.
Does everything that you've set up until now mean that our planet is one of the earliest in the universe that could support life?
That's an incredibly interesting question. The sun came to be in cosmological frame quite a long time ago. No? Like 5 gigayears ago, when the universe was about half its age. And we even think, and then the metal content was already relatively large. We actually think that, I think the current record holder of a star that we have found a planet around has, I think, 1/50th of the metal content of the sun. So it means that we were not the first ones. And I think there were probably significantly other solar systems in the Milky Way that were able to harbor life, that were able to make rocky planets. Now, of course, there's the issue that, we always define life as we know it, in the sense of, the planet has to be relatively far away from the star so that water in liquid form could exist. Now I would argue that it has to have the right content of heavy elements so that a magnetic field could exist. And there's many, many kind of conditions that need to happen in order for a planet to harbor life. But probably there were other solar systems much earlier than ours that, before we came to be. Whether or not it could have harbor life, that's an interesting open question. But of course, we define life as we know it. But I'm sure, biology has found incredibly intelligent and different ways of making life, somewhere in the galaxy. So very different to ours.
Well, it's been a pleasure sharing atoms and ideas for the past hour and a half.
Thank you
Please,
so
once
much for
again,
having me.
thank Dr. Enrico Ramirez-Ruiz.